This is Math 30-1, and today we are starting into Chapter 5, which looks at exponential and logarithmic functions. So to begin with, I have a page here that you have in your notes that I'd like you to work through as you review working with exponential expressions. So see how you do working through this page, these 14 questions. So once you finish these, you can restart the video and then have a quick look at my solutions, and then we'll continue on. So you can pause the video now to do these questions, please. Well, here you can see my answers to the questions, and I'll go very quickly over them. Number one, simplifying, we would just say is 2 to the 8th. So evaluating, we would say is 256, but I wrote both of them here. So you remember that when we're multiplying powers with the same base, we can add the exponents. Because here we're saying that I have 2 as a factor 5 times, and then here I have 2 as a factor 3 times, so in total I have 2 as a factor 8 times. So that's where the 2 to the 8th comes from. Similar idea in number 2, where we just add the exponents. Remember, there is an invisible exponent of 1 with this last x. That's how we get 13 as our exponent. When we're dividing powers, this tells me I have 5 2's multiplied in the numerator, 3 2's multiplied in the denominator, so 3 of them cancel out between numerator and denominator. I'm just left with 2 in the numerator. 2 squared is 4. Number 4. Similar idea, but now we have 5 in the denominator. So we could write this in this way. And if we did, then it's pretty easy for us to see how the 2's are canceling out. So these 2's all cancel. I'm still left with a 1 in the numerator. So keep that in mind. There's always a factor of 1 there, but I have 2 2's in the denominator, which would be the same over as 1 over 2 squared, which is what I wrote here. But if I use that rule of subtracting exponents, then I would do 2 to the 3 minus 5, which is where we get this 2 to the negative 2. So there we can discover that 2 to the negative 2 is exactly the same as 1 over 2 squared, or 1/4. So where a positive exponent, like this, means I have repeated multiplication, a negative exponent like this means I have repeated division. So that's why the 2's are repeatedly showing up in the denominator. We can do the same thing with variables, and that's what we have in question number 5 here. Subtract the exponents. And with number 6, again, subtract the exponents. Often when we're asked to simplify, what we want to do is go as far as getting an answer with a positive exponent. And so that's why I rewrote this a to the exponent negative 7 as a 1 over a to the positive 7. Simplifying often means, not always, but you can expect that it'll likely mean we want a positive exponent. For question number 7, here what we have is a power raised to a power. So I have this 2 to the exponent 4, but this repeats 3 times. That's an exponent of 4. So since this base is repeated, again, now I can look at it as multiplication. With the same base, I add the exponents. 4 plus 4 plus 4 gives me the 12 in the exponent. And that probably reminds you of that shortcut. When we have a power raised to an exponent, we can multiply these two exponents. So the 4 times 3, and that's where we get the 12. Question number 8 is similar but a little bit different. And here, what I want to point out is that this 2 has an exponent of 4, but if there's no bracket around the negative 2, as in we don't have negative 2 to the 4th. So that's not what we're given in this question. So if we have a negative and then 2 to the 4th, it's only the 2 that's repeated 4 times. The negative is like a factor of negative 1 that's separate in front. So when I evaluate it, the 2 times 2 times 2 times 2 is 16 times the negative 1 gives me a negative 16 to the exponent 3. And then we could evaluate that as well. and that would give us negative 4,096. Again, now we have a negative to an odd exponent, so we do get a negative answer. Let's continue on. Question number 9, similar idea. This time, if we simplify this inside part, we'll get a negative 8 to the exponent 4, which will end up giving us a positive answer in the end. Now what I did in blue is a little bit different. Again, I recognized that since I had this negative here, and I had an even exponent out there, I knew that the negatives would end up canceling out, because that means I have 4 negative 1s multiplied together. So I ended up just ignoring the negatives, and then I multiplied these exponents. And again, if we evaluated, we would get 4,096, as we did in question 8. Now, when we're asked to simplify and we have a mixture of numbers and variables, typically that means we want to evaluate the numerical part and then just simplify the variable part. So here, when I have this base, notice this 2 is part of the base, so it gets this exponent of 6 applied to it as well. So that's why we get the 2 to the 6, which gives us 64. And then I can multiply this 3 and the 6 to give me the 18 as the exponent for the b. And that would be our simplified answer for question number 10. Question 11. So a reminder that I said that a negative exponent up here tells us that we're going to do repeated division. Another way for us to think of it is it's telling us to take the reciprocal. So you'll notice this base, 2 over 3. That negative means I take the reciprocal, and so it becomes a 3 over 2, but now I have a positive exponent up here. So I got rid of that negative exponent by flipping or taking the reciprocal of the base. Then this exponent and that exponent of 1 each get the 3 multiplied to them, and that gives us 3 cubed over 2 cubed, 27 over 8. Question number 12, jumping in complexity. I did it in steps again. Often what I like to do is deal with the negative exponent out here first. Now what I could have done with this question number 11, maybe I'll come back here, is what I did in blue, I could have done as my first step. So I could have written that original question as 2 to the negative 3 over 3 to the negative 3. But personally, I'm not a fan of having a whole bunch of negative exponents, so I tend to avoid this. It's not wrong. It's perfectly correct. And in this case, what the negative exponent tells me is I take that power to the other side of the fraction. So this 3 to the negative 3 moves to the numerator, becomes a 3 to the positive 3. This 2 to the negative 3 moves to the denominator and becomes a 2 to the positive 3. And I get the same thing as I did using the other method. So here I could have done that. I could have taken this negative 2 exponent, multiplied it to this 1 to the 5, to this 1, and to the negative 3. But then I get a bunch of negative exponents, and I'd rather not. So I chose not to do that. I started by doing the reciprocal of my base, and that gave me a positive exponent out here. Then I took this 2 and I multiplied it to the 1 to give me a 2 in the exponent for the 4. I multiplied it to the negative 3, which gave me the negative 6 in the exponent for the y. And I multiplied it to this one in the exponent from the 3, which gave me 3 squared, and then times this 5, which gave me the 10. And then I just evaluated the numerical parts. 4 squared is 16, 3 squared is 9. But then, because I had this negative exponent in the numerator, I took it to the other side of the fraction and gave it a positive exponent. On to the last two. A reminder here that a fractional exponent means that we have a radical. So the number that's in the denominator here is the index in our radical expression. The number in the numerator would be still an exponent that would apply to the entire thing, and we'll see that more in number 14. So we could just rewrite it like this, and then we do the cube root of 64, and that gives us 4. Or we could say, well, 64 is the same as 4 to the exponent 3. 4 cubed is 64, and then I could multiply these two exponents, and I get an exponent of 1. I like this method because it's easier on my brain. I don't like thinking cube roots, but this is easier for me. An alternative would have been to say that 64 is 2 to the exponent 6 and raise that to the exponent 1/3. Then again, power raised to an exponent, I multiply those exponents and I get a 2 squared, which again gives me my answer of 4. Question number 14. Again, I chose this method here where I rewrote this base, the 27, as a power with an exponent of 3. So I have 3 cubed, all to the exponent -4/3. Then I multiplied these two exponents. Again, this isn't the only way to do it, but because this may be a little less familiar, I chose to do it for this question. That gives me a -4 in the exponent. I take the reciprocal, give it a positive exponent, and then evaluate to get the 1/81. So that reviews the exponent laws that you've learned in previous grades. Let's get into exponential functions. First, though, a reminder of the terminology. When I have a number raised to an exponent, we call that entire thing a power. Now, some teachers will say that this little n that's up here is a power, but I find that confusing. So how can this n be a power, but then this whole thing also be a power? So for many teachers, especially in Canada, what we do is we make the distinction and we say that little number up there that's superscripted is an exponent. And the x we would say is the base. So I have a base to an exponent. The whole thing is a power. I wouldn't say the n is a power because that's confusing. And I try to keep each term referring to only one piece in this expression. If you call it a power, that's fine. Many excellent teachers and mathematicians do. I just prefer not because I think it's confusing. Well, this was supposed to be a warm-up question, but I wanted to go over that with you. The rest of this page is warm-up until we get to a definition at the bottom. And so I'd like you to pause the video at this point, work through the next 3 questions. Once you finish, restart the video, and then see what I ended up with. Okay, so pause the video now. So for number 2, there's how I got my table filled in. And you can see the points on the right that form this pattern that curves up as we go to the right. That's representing these points. I'd get a similar set of values in my table and a curve that goes in the opposite direction in question number 3. So we'd say that both of these are exponential. The blue one we would say is exponential growth because as we go from left to right, our y values are getting bigger. And the red one we'd say is exponential decay because as we go from left to right, the y values are getting smaller and smaller. Now here we just plotted a series of points, but this is actually a continuous smooth function for both of these, and this is what the graphs would look like. So all the points would connect. And as you look at this, hopefully you can observe a few things. Even though we have the graph looking like it stops at the end here, it does continue on to the left forever, looking at this blue graph, and it's going to continue up and to the right forever. And so the domain for this function will be all real numbers. So when I have a function written in this form, here we said x could be any real number, and that is always the case, with the exception of some application questions that'll put in restrictions for us. Similar idea for this decay function. The domain is all real numbers. So the graph continues up and to the left forever, and it continues to the right forever. And you'll notice that we have a horizontal asymptote here along the x-axis. So the graph never actually reaches a y value of 0. So when you filled in this chart for number 4, you probably found, hopefully, that it's exactly the same for both of these functions. So the first function, we had a base of 2, and the second function, we had a base of 1/2, reciprocals of each other. And so the impact was growth for this first function, decay for the second one. But the domains are the same, all real numbers. Ranges are the same, y is greater than 0. Neither of them has an x-intercept. They both have a y-intercept at 0, 1, and they have a horizontal asymptote, which is y equals 0. Number 5. How would the graph of y equals 2 to the negative x compare to the graphs above? Well, if you think back to what we talked about in the previous questions, that negative exponent I could write as a 2 to the negative 1, which is a 1 over 2. So this function, where I have a negative exponent, is going to be exactly the same as this red function that we had above. Now we could look at it as they have different bases, or we could look at it and say, this negative, what does that do if I have a negative sign with the x? That changes x's, which means it's a reflection in the y-axis. So as we look back up here, we can see that the red graph is a reflection in the y-axis compared to the blue graph. We get that by doing the reciprocal of the base, or by putting a negative in the exponent with the x. Well, this introduces exponential functions. They have this form, y equals b to the x, where b, our base, has to be greater than 0, and it can't equal 1. Well, why is that the case? Let's have a look at Desmos and see what Desmos shows us as we look at this function y equals b to the x. And here I've started with a b value of 2. So as I adjust my b value, well, first let me have it get bigger. You'll notice as that base gets bigger and bigger, my graph grows more quickly. So it gets steeper and steeper on the right side. And as that b value gets smaller, you'll see the graph grows more slowly until I get to a point where my b value would equal 1. Well, here I don't have a curve anymore. I just have a horizontal line. Why? Because 1 to any exponent is always equal to 1. So we would say this is not an exponential function. That's why we put on a limitation that the b value cannot equal 1, because then we have a linear function. We don't have an exponential function. Well, what if our b value gets smaller? Well, as it gets smaller, you can see, oh, now we have this decay function. So if our b value is between 0 and 1, we're going to have the graph decreasing. And the closer our base gets to 0, the more quickly that graph decays. Well, what would happen if the b value was 0? Well, here I get a array, we might call it. So a graph that begins at 0 and then goes to the right. Again, this isn't exponential. It doesn't have that exponential curve, either growth or decay. So again, we'd say this is kind of linear, but there's a restriction on the domain. What happens if I get a negative number in my base? Well, here you can see a few points. There's a point up here. Maybe if I click on this, that'll help. Yeah, so you can see there's a point there, a point here, there, there. And these points are actually bouncing above and below the x-axis. And as I continue this going, here you can see even more. So we can see there's a point down here as well. And as I continue, oh, so there's a point up here, then one there, one up there, one down here. And depending on the resolution of your screen or even on your calculator, if you were to enter it there, we get these points that jump above and below, but we also get these gaps. It's not a smooth, continuous curve. Now, there are values in between here, but they aren't being shown. But still, there are gaps in between some of the values that are in between there. So it's just a confusing graph. And so we'd say that if we have negative b values, it's not going to give us that predictable exponential function form. So instead, we get points jumping around, not something particularly useful. So that's why we have these restrictions on this exponential function. The base has to be positive, and it can't equal 0. Well, the next page kind of ties into what we just looked at. So I'm just going to quickly go through 6, 7, 8, and 9. So here in question number 6, I have a base of 3, and then for number 7, a base of 1/3. What do you expect the graphs to look like? Well, hopefully you thought they will be reflections in y equals, or in the y-axis, where if I have the base of 3, I'll have exponential growth, my blue function. If I have a 1/3, exponential decay, my red function, and they're mirror images in the y-axis. If I have a larger base, then my graph grows more quickly, or if my base is closer to 0, my graph decays more quickly. So here's what the 4 graphs look like together if we put them all on one grid. And you can see that this y equal 10 to the x grows the quickest as we go from left to right, and then the 3 to the x grows more slowly. And again, the base of 10 and the base of 1/10 mirror images, reflections in the line x equals 0, which is the y-axis. So in summary, when the b value is greater than 1, we would say the curve increases more sharply as b increases, and we call that exponential growth. If our b value is between 0 and 1, then the graph decreases more sharply as b decreases. Now, we're saying this with the assumption that our function has the form y equals b to the x. Now, what you know from chapter 3 is that we could perform all sorts of transformations to this function, which will change how it looks. So we could do reflections that would say, oh, if I have a b value greater than 1, it may still be a decreasing function if there was a reflection. So we need to watch for those kinds of things, and that'll come up as we look at more examples. But first, the summary of transformations. We have looked at this many times in this course. So here, first of all, in this first column, we have that standard generic function where if y equals f of x, what does the a, the b, the h, and the k, what do they do to our function? Well, why don't you pause the video here and complete this first column. And you may want to complete the second column because it's basically the same idea, but notice I've changed some letters. Here, b is the number that's going to describe my reflections in the y-axis and my horizontal stretch. Here I changed it to a c because we're already using the variable b to represent the base. Okay, so just be careful that I've used a different variable up there when it comes to horizontal reflections and stretches. You can pause the video and then restart when you want to compare with my answers. Here we go for the generic function. And it looks essentially the same for the exponential function. So all those transformations that we did in chapter 3, we can now apply to exponential functions as well. Again, taking note that here I'm using c's instead of b's because here I used a c in this equation. So do you need to know this equation? No, you really just need to know the chapter 3 equation and then be able to apply it to an exponential function. So let's do that with some examples. Here for each of these examples, we want to describe the transformations applied to y equals 3 to the exponent x. So we're going to say this is our starting function. Next, we'll state whether the graph increases or decreases, and then we'll talk about the equation for the asymptote. So as you look at this equation, you'll notice, oh, well, it's almost identical. We just have a 2 that's multiplied out in front. So what does this 2 in front do? If you said vertical stretch, you are correct. And that's all we have for transformations. So if I have a vertical stretch, then my graph is increasing because my b value is greater than 1. Next, equation of the asymptote. Well, because k is 0, I haven't added or subtracted, my graph hasn't been translated up or down, my horizontal asymptote is still y equals 0. So it's a little bit like with sinusoidal functions, that center line didn't move unless we had a k value to translate the graph up or down. Here's going to be the similar idea where the asymptote won't move unless we have a k value that's not 0. On to question 11. Why don't you pause and fill in number 11, and then I'll walk through it with you. Well, now we only have something multiplied in the exponent, but it's negative, which means I have a reflection. It's with the x's, so it changes x's, which means a reflection in the y-axis. And then there's a horizontal stretch by a factor of 1/4. So again, remember that horizontal stretch factor is the reciprocal of that coefficient of the b, the absolute value of that number. Is the graph increasing or decreasing? Well, my b is greater than 1, which makes me think increasing, but then this negative in the exponent tells me I have a reflection. So if I was to do a rough sketch here, oh, we should have a y up there, shouldn't it? Well, my rough sketch of 3 to the x would curve sort of like that. But then as soon as I have a negative in the exponent, let's suppose I just did a 3 to the negative x, that's going to be a reflection. This will be an invariant point. This point that was up here increasing is now going to be up here on this side, and my graph will decrease and curve in this direction. So now, even though my b value is greater than 1, my function is decreasing because of that reflection. Again, there's no k value, and so the asymptote is still y equals 0. Try number 12, and then restart the video when you want to see my solution. Well, because we just have numbers added and subtracted in there, we just have translations. There are no reflections. Our base is greater than 1, so our graph is increasing. But now we have a uh, oh, an asymptote, I should say, a horizontal asymptote of y equals -6 because my whole graph moved down 6 units. You could enter it into your calculator to have a look just to compare and confirm that that is the correct description for these 3 parts. Second last, number 13. Again, pause the video, try this question, and restart when you're ready to compare with my answer. Reflection in the x-axis, horizontal stretch by a factor of 1/2 because of that 2 multiplied in the exponent, vertical stretch by a factor of 1/2 because of the 0.5 out in front, and again, remember the negative is the reflection, it's not part of the stretch. And then we have translations left and up. Now this time, again, we have a b value greater than 1, but this reflection in the x-axis means our graph will be decreasing. So here's what it might look like. Well, there's a rough sketch of y equals 3 to the x. If I just put a negative in front, remember that negative is not part of the base. We can imagine that we have a bracket here and there. So the 3 to the x has that negative 1 multiplied to it. That negative 1, a reflection in the x-axis, so my graph would curve down like this. So as I go from left to right, my graph is decreasing. Finally, that plus 8 at the end gives me my horizontal asymptote. Then as we look ahead at question number 14, remember that key piece of information, which is, if there's a coefficient to the x, we need to factor that out, or our horizontal translation will not be correct. So our first step is to factor that out so that we can get our horizontal translation, which will be to the left by 3 units. Increasing because the base is positive, no k value, so y equals 0. It's our horizontal asymptote. And there's the introduction to exponential functions. Some questions for you to practice here. A camel and drums, a spectacular sound sensation that you can't get over a video. So sorry, you're going to have to wait till we're in person. There we go. That is the introduction to exponential functions. I'll see you again for the next lesson.